Okay, Algebra 2 students, today we're going to draw scatter plots and best fitting lines and kind of talk about those kind of things. We're going to relate this to our discussion of linear equations, slope, things of that nature. So what I want you to do is maybe pause this video and take like 20 to 30 seconds, and these three pictures we have here, I want you to just write a couple things. What do you notice? What do you wonder? Now you might have noticed, well, there's just a bunch of dots in each of these pictures, but in the first picture it seems like these dots are trending downward. In the second picture, it seems like the dots are trending upward. The third picture, it doesn't seem like they're trending in any direction. Now, if we used a line of best fit, or kind of approximated what was going here, if I were to draw a line in each of these, well, in the first one, it looks like that line would be decreasing. It looks like its slope would be negative. In the second one, it looks like the line would be increasing. It looks like its slope would be positive. The third one, it doesn't really look like I could use a line to approximate what's going on here. So in the first one, well, these dots, or this scatter plot, we would say it has negative correlation. We would say the second one then has, well, the slope of this line would be positive if you approximated it, so it would be positive correlation. And this one would be no correlation. Okay, well, let's describe what does positive correlation really means. Well, if you have a graph here, we're working with a y and an x-axis, kind of similar to slope, we would say, well, it's positive correlated. It has positive correlation if y tends to increase as x increases. Okay. Well, for negative correlation, it's basically going to be the opposite of that, and I need to learn how to spell increases. Increases. In negative correlation, you would say, well, y tends to decrease. As x increases. So basically, another way you can remember this, well, if it seems like you put a line in there and it has a positive slope, you'd say it's positive correlation. If you use a line to approximate it and it's trending downwards, it looks like it has a negative slope, you'd say negative correlation. So all we're going to do is describe the correlation of a scatter plot. So this is actually a pretty popular graph a couple years ago. So we have the number of ice creams sold, that's our y value. We have the murder rate in New York. And it seems to be, well, what kind of correlation does it seem to be? Does it seem to be positively correlated, negatively correlated, or no correlation? And if you were to draw a line here, it probably looks something like this, right? Okay, well, it seems to be, or seems to have positive correlation, right? Okay, but let's talk about correlation and causation. Well, as the murder rate goes up, so does the number of ice creams sold, or as the ice creams sold go up, so does the murder rate. So does the murder rate cause ice cream to be sold? If someone gets murdered, is the chance of buying ice cream more likely? And that's the problem with correlation. Here's an important thing. Very clearly, these two things are not related. They are correlated, but they're not related. It doesn't necessarily mean one causes the other. So just because things are correlated does not mean they cause one another. Correlation does not imply causation. That just basically means if two things are correlated, they're not necessarily causing one another. There could be other variables that aren't explained here. Maybe the murder rate goes up in the summertime, and maybe ice cream sales go up in the summertime. There's some variables that you necessarily aren't comparing here. So just because two things are correlated does not mean they cause each other. But this one, if you were just looking at the graph, if you omitted everything else, well, it seems to be positively correlated. Okay, well, things have, like, you can say the strength of their correlation, how strongly they are correlated. And that is, the way you can show that is by talking about something called the correlation coefficient. The correlation coefficient. It's also denoted by R. Let me zoom in here so my writing's a little bit better. Maybe not. Denoted, there we go. By R. It's just a number from -1 to +1 that measures how strongly it's correlated. How strongly data is correlated. Correlated. Okay. If your R value is 0, that means there's absolutely no correlation, or seemingly no correlation. Okay. If you have an R value of 1, that means there's strong positive correlation. And if you have a -1 value, you have strong negative correlation. Okay, so if you're at 0, there seems to be no correlation in the data. 1 means there's strong positive correlation, and -1 means there's strong negative correlation, which leaves us a lot of leeway in these areas, right? Between 0 and 1, between 0 and -1. So you can have things that are seemingly positively or negatively correlated, but maybe not strongly so. Like maybe they generally trend downwards, but they're not like in an exact line. That would probably, well, the closer you get to -1, the stronger negative correlation it has. If you have a value of -0.5, it'd be about, you would say it has weak negative correlation. It has like a positive of 0.5, you'd say it has weak positive correlation. So the further you get to that 1 value or negative value indicates how strong the positive or negative correlation is. So to estimate correlation coefficients, well, we want to tell whether the data correlation coefficient for the data is closest to -1, -0.5, 0.5, or 1. And this is basically your best guess. But you can kind of infer a little bit here. Well, let's start with this middle one. Clearly, well, if I were to draw a line, it doesn't really look like it's trending upwards or downwards. I would probably argue this one has no correlation, seemingly. And, well, that would be an R value of 0. This one on the left, well, it seems as my X values increase, my Y values decrease. If I were to draw a line to approximate this, it would be a negative line. Now, those dots kind of hover above and below that line I've just drawn arbitrarily. So I wouldn't say it's necessarily strongly correlated, but it is negatively correlated, right? There seems to be negative correlation, but not necessarily really strong. It's not exactly in a line. So I would say, well, this has somewhat negative correlation, which, well, if you were to use an R value, you'd probably say R is about, well, somewhere between 0 and -1, but not really that close to -1, because -1 indicates, well, it's really strongly correlated. I'd say R is about -1/2, right? That'd probably be the best approximation. And then finally, our third one here. Well, this one, very clearly, if you draw a line, it's going to be a positive line. So we know there's seemingly positive correlation. Is it strongly correlated or is it weakly correlated? And this one is probably more strongly correlated than the first one. So I would argue some value close to 1, not necessarily exactly at 1, because 1 would basically indicate a straight line, but I would argue, well, close enough to 1. So I'd say there's strong positive correlation. And your R value would probably be about 1, right? Maybe a little bit less than 1, like 0.99 or 0.95, I don't know. But approximately 1. Okay, so just visually you can kind of estimate the correlation coefficients. We're going to talk a little bit about how to use your calculator to actually find the correlation coefficient. But for right now, that's just graphically, you can kind of estimate. All right, now we want to approximate a best fitting line. This is where the stuff we've done before, finding the equation of a line, comes in handy. But we'll just start with this. We have this table, and it shows the number Y in thousands of alternatively fueled vehicles that are used in the United States, X years after 1997. We want to approximate the best fitting line for the data. So we have these X values that indicate the years since 1997, which means, well, at the year 0, it's 1997, 1 is 1998, so on and so forth, right? Okay, and the Y values represent, well, in thousands, how many alternatively fueled vehicles there are. So there's apparently 280,000 in 1997, and then, well, seemingly as the years increase, so do those y values. But let's graph those. I already wrote my scale out, so I'm going to go by ones on my x-axis. Now, if you look here, I don't necessarily like have a scale going from 0 to 550, but I have this little zoom in here, this break in the graph, kind of like a lightning bolt, which means, well, I'm going to skip some values, but I'm going to start at 250 because my least value is 280, and then I go all the way up to 550, so I'm going to count by 50s. So I just do a break or a jump in the graph to show, well, I'm going from 0 to here, but there's a jump. And I'm just going to plot these points. So at an x value of 0, I have 280. It's about there. X value of 1, I'm at 295. I encourage you to pause the video and maybe write these out on your own. 1 has 295. 2 has 322. 4 has 420. Whoa. 2 has 322. Okay, 3 has 395. I skipped that one. 4 has 425. 5 has 471. Be about there. 6 has 511. Be about there. And 7 has 548. So, it seems like this has positive correlation. Now we want to approximate the best fitting line for the data. Well, basically you want to choose 2 points that would best fit this line and use those 2 points to make an equation of the line. So I'm going to choose, well, you typically kind of want to choose the best values that would fit the line, and this is really where it's a matter of opinion. I would choose this point. I'm going to choose 1, that x value of 1 and y value of 295, and I'm going to choose this y value of 548 with an x value of 7. So I'm going to go through this point. I'm going to go through this point. Okay, that's the line I'm choosing. Okay, so here I have a value of 1, or excuse me, that's 2. I want to go through 1. Let's try this again. Right, this point and that point up there. So I'm choosing the point 1, 295, and 7, 548. Okay, so I have 2 points. Well, basically, this becomes the same exact problem as you've seen before. Given 2 points, 1, 295, and 7, 548, find the equation of the line. Well, you know, to find the equation of a line, what are the 2 things I need? And I've said this so many times, you guys should know, well, I need, for an equation of a line, I need a slope and a point. A point and a slope. Well, what formula might you want to use? Well, point slope. But let's start by finding that slope. Now, if I have these 2 lines, remember that you can find the slope. Slope is change in y over your change in x values. Well, with these specific y, or these specific points that I've chosen, you could choose any 2 points that would kind of approximate the line. You have to be careful. Like, occasionally there's outliers. Like, I could possibly have a point that is like way down here, and I probably wouldn't choose this point to make a line because it's not going to best represent the data. So make sure you're choosing points that kind of make sense. But in either case, choose your 2 points, find your slope. Well, change in y values over change in x values, the difference of my y values, 548 minus 295, over my change in x values, 7 minus 1. Well, the denominator is easy to find, that's 6. The numerator is 253. This gives me a slope of about, I'm going to approximate to the nearest tenth, 42.2. So that's my slope. Well, I have a slope, I have a point and a slope. What formula can I use to write this equation? If I have a point and a slope, yes, you're probably screaming to yourself, point-slope formula. Remember, y minus y1 equals m times x minus x1. Just plug in your information. So I have y minus y1. Choose either point value, it doesn't matter. I'm going to choose this value here. So my y value then becomes, well, 548, subtract that y value. It's equal to your slope, which mine was about 42.2, times your x value, minus x1, which is 7 in this case. Okay, simplify, distribute that 42.2, I'm left with y minus 548 equals 42.2x, minus 42.2 times 7 gives me negative 295.4. Simplify, isolate that variable y, add 548, add 548. You're going to get y equals 40, oh my goodness, I forgot the x here, 42.2x. It's going to equal 42 and 2/10x plus 252.6. I now have a function that represents this data table where, well, for any given x value, remember x represents the years since 1997, I can find, well, approximately how many alternatively fueled vehicles there were in that year. Okay, so using this equation, in example 4 here, using this equation we just created, we want to predict the number of alternative fueled vehicles that were used in the United States in 2010. Okay, remember x stands for your years, but you want to be careful. It's not your years in like terms of the year you're given, right? Remember your x values are terms of years since 1997. Okay, well, you have to think, what is your x value? Since it's 2010, well, how many years has it been since 1997? Remember in 1997 it's 0. Well, in 2010 it's 13 years since that value, since 1997, which means your x value is going to be 13. So all you do is, well, you have your function f of x equals 42.2x plus 252.6. This was the linear equation I created. If you chose 2 other points, you'd have a similar one, probably slightly different looking equation. That's perfectly fine. We want to use this to approximate, well, when we have an x value of 15 years, that's like saying, well, what is f of 15 then? So f of 15 becomes 42.2 times, well, instead of x, I replace that with 15, plus 252.6. Plug that all into your calculator. You get about, well, 801,000. Right? Remember, this is in terms of thousands, so I'm just going to write that. 801,000 cars that were alternatively fueled. Now, that's how you would do it algebraically. You're going to need to know how to find the slope of a line through 2 points. Basically, this is like a review of, well, section 2.4 whenever we're writing equations of lines. And if you're given a data table, well, you can choose 2 points, and you can just create an equation of a line through those 2 points like you would in any other problem. Then using that, we can extrapolate from there. That's the value of finding this linear equation, is we can then predict, assuming this relationship is linear, well, in any given year, how many cars would there be? And again, there's going to be some limitations with this because, well, you can't have a negative value of cars, or really, I guess you could years relative to 1997, but for your y values, it doesn't make sense to have a negative value. So it has its restrictions, but it is a pretty good line. Now, another way that you can find this, and I want you to know how to do this, is you can use your TI-84s. So get that out either using your phone or your laptop, or if you absolutely need one, grab one from the back of the room, but make sure you sanitize it. And here's what you can do. You can have your calculator give you a line of best fit. So if you get out your calculator, here's what you need to do. Keeping that table, and it looks like it disappeared on me, so hopefully you have it written down. But you get out your calculator, you click on, obviously. This one is not turning on. Come on. That was weird, but now I have one that's working. Here's what you need to do. You click Stat, and you click Edit. So Stat, and then just click Enter, Edit, and it gives you these lists. What you want to do is treat that L1 list as your X values, treat that L2 list as your Y values. So I'm going to go in, I'm going to type in my X values. Well, I have an X value of 0 for 0, 1, 2, so on and so forth. So enter your X and your Y values. Okay, and then enter your respective Y values. So arrow over in the L2 list. I'm going to enter my Y values. So 280. This doesn't quite work with my keyboard. That's okay. Goodness. 2 clear. 280. 295. 322. 395. 425, 471, 511, and 548. Okay, so now we basically have this data table, and you can graph it as a scatter plot. But if you want to do that, all you have to do is exit out of the window when you're done entering your x and y values. Go up to y equals like you're typing in a graph, but then click plot 1, and you have to go up there, click enter on it, and highlight it. Now it's going to plot those data points. And this part is basically optional, but you want to see what the shape of the graph is before you use a regression model, which we're about to do. We already know it's seemingly linear because we've graphed it by hand, but let's assume we haven't. We don't necessarily know what this is going to look like. I'm going to adjust my window because right now my minimum x value is negative 10. I want that to be 0. And I'm going to adjust my scale kind of like we did on our graph. I'm going to go to probably 10. 10, and then counting by ones is fine. Now our y values, we're going to probably go from 250 like we did on our graph to a maximum of 550, and we're going to count by 50s again. So this should look a lot like the graph we've had. So adjust that. Remember, this is the window button. I just clicked there to adjust this, and then I'm going to click my graph button and graph it. Now, does this seem to be a linear relationship? You would say yes. And this is a technique that you guys want to know because we're going to use this regression model for like quadratic functions, things like that. This is a somewhat optional thing to do to look at the graph, but I strongly recommend it because in the future we're going to say, well, is this a linear relationship, quadratic, trigonometric, so on and so forth. Well, this one's clearly a linear relationship. So what you want to do is we want to find our line of best fit. All you do once you've clicked stat and edit, once you've entered this list, which we have here, is go back to stat again, and then use your right arrow key, arrow over, and there's a bunch of regression models we're going to do here, or that you can do here. Okay, you'll arrow down, you'll see lin reg, that means linear regression, 5 quadratic regression, cubic regression, quartic regression, so on and so forth. There's a bunch of different regression models. Now we know it's linear, so we're going to click enter on number 4. We want a linear regression model. So it's saying what's your x list? That's L1. What's our y list? We let that be L2. We're good on those. Enter, enter. Frequency list, don't worry about that. Don't worry about the rest. We're just going to click enter on all of these. We're going to click calculate. And it gives us this equation, y equals ax plus b, where your a value is 40, your b value is 262. So your calculator, it's coming up with an even, this is probably a better linear regression since we just chose 2 points, so your calculator is going to be a little bit more accurate. It's saying, well, our linear regression model using this calculator would be 40, about 41, or 40.8. plus 262.8. So 40.8, 262.8. So using the linear regression feature like that, well, we would say y equals, what was it, 40.8x plus 262.8. That would be your linear equation. I want to double check that because I don't remember if it was 40 or if it was 42. Yeah, 40.8, 262.8. Okay, now in the future, we did just talk about our R value, our correlation coefficient, which tells us, well, how strongly positively correlated something is, how strongly negatively correlated something is. Okay, you can use your calculator and actually find that value. Now, mine didn't give it to me, and yours probably doesn't either unless you do this. If you want it to give you that correlation coefficient, what you have to do is go to your catalog, which you get by clicking second, 0, catalog, and then you want to scroll all the way down to, it's called diagnostic on, diagnostic off. You can just jump there because the list's quite long by clicking alpha D. So alpha D, enter. That's not what I wanted. Try that again. Second, catalog, alpha. Oh, it already starts with alpha. Alpha, and then D. And then scroll down to diagnostic on, which my computer's processor isn't super great, so my calculator's running slowly. Click diagnostic on, enter, enter. And now when you run your regression models in the future, whether you're doing a linear one or a quadratic in the near future, click stat, calc, linear regression again. But this time, what it's going to do is it's going to give us some statistics. And it gives us an R value of 0.992, which means this linear equation it's came up with, 40 0.8x plus 262.8. Well, that is, according to your R value, is very, very strongly correlated. It has a R value of 0.992, which is essentially 1. Strongly positively correlated. Now that R squared value is also another useful tool. That value tells you how well basically this regression model works. And it works, your R squared value, well, it's literally taking your R value and it's squaring it. So you're only ever going to have a positive value with your R squared. And your R squared tells you how well this model works. So our data is very clearly linear, and the closer you are to 1, the better your model fits the data. Well, this linear model fits the data. It has an R squared value of 0.98. R squared and R are slightly different. R basically tells you it can be negative, but it just tells you whether it's strongly positively correlated or negatively correlated. R squared just tells you essentially how well this model fits the data. How well this model fits the data. In the future, we're going to talk about quadratic models, so on and so forth, exponential. And that's where R squared will come into play more then. We'll talk about that in the future. But that's how you would use your calculator to find a linear regression model. Make sure you still understand how to choose 2 points, construct a line through those 2 points. How to find the equation of a line through 2 points, essentially, here. All right. That is all we are going to have time for today. Good work, everybody. And remember, as always, stay safe out there.